In artificial intelligence, language models generally fall into two broad categories: static models and self-learning models powered by reinforcement learning. While both types generate text and provide intelligent responses, their underlying mechanisms, computational demands, and real-world applications differ significantly. A static model, like most commonly available AI models, is pre-trained on vast amounts of data and then frozen. Once deployed, it no longer learns, updates, or adapts to new information unless it is explicitly fine-tuned with additional training. These models are highly efficient for tasks like content generation, customer support, and general-purpose reasoning because they can run on relatively modest hardware. They require only inference, meaning they simply process input and generate an output based on patterns they have already learned. This makes them widely accessible, as they can function well on consumer-grade computers, cloud services, and even mobile devices in some cases. However, their limitation is clear: they do not improve over time. If new information emerges after their last training update, they will not integrate it unless retrained. In contrast, a self-learning model, sometimes referred to as a model with embedded reinforcement learning, operates dynamically. It continues to refine its responses through feedback mechanisms, adjusting its behavior based on rewards and penalties. Instead of merely recalling patterns from training data, it actively explores possible outputs, iterating and improving over time. This process requires a far more complex computational framework, as these models must evaluate actions, adjust strategies, and optimize outcomes based on real-time interactions. Running such a model is exponentially more resource-intensive. Unlike static models that rely purely on pre-trained weights, self-learning models engage in ongoing computation, necessitating powerful GPUs, extensive memory, and in some cases, specialized infrastructure to manage reinforcement learning loops. This is why models like DeepSeek R10, which incorporate reinforcement learning, tend to be significantly larger than their static counterparts and are not yet easily available in lightweight distilled versions. For personal users, the implications of these differences are considerable. A static model is more practical for everyday tasks, writing, coding assistance, summarization, without requiring dedicated hardware or ongoing maintenance. A reinforcement learning-powered model, on the other hand, would be ideal for complex decision-making, autonomous systems, and adaptive AI applications, but at the cost of greater computational expenses and setup complexity. Businesses seeking to deploy AI at scale must weigh these trade-offs carefully. While a static model offers stability and predictability, a reinforcement learning model could provide a competitive edge by continuously optimizing responses, improving decision-making, and adapting to real-world scenarios. Ultimately, the distinction between static and self-learning models isn't just about how they function, but also how they integrate into workflows and business strategies. Static models are easier to deploy, but limited in adaptability, while reinforcement learning models offer long-term intelligence at the cost of complexity and resource demand. As AI research advances, we may eventually see smaller, more efficient reinforcement learning models that bring adaptive intelligence to a wider range of users. Until then, choosing between these two approaches depends on balancing performance, cost, and long-term scalability.